In this recording, we will discuss startup of a mixed flow reactor. Mixed flow reactor. So we added the missing term here. The balance equation that we have learned already is on the board. It is the time rate of change of total number of moles of species A within the system boundaries. That is equal to the net rate that component A enters through the system boundaries minus the net rate with which the component A leaves through the system boundaries. And this term represents the consumption of component A within the system boundaries at a rate indicated by RA. V is the volume of our reactor. Now I'm going to define, remind you, the two new terms. One is the volumetric flow rate of the components that is coming in and out of the reactor, and rho represents the density of the fluid. They are both going to be treated as constants. They are not going to change. The reason that I bring this up is that I'm going to write an overall material balance, total material balance. The time rate of change of total mass within the system boundaries is going to be equal to the net rate that mass flows into the reactor minus the net rate that mass flows out of the reactor. I'm going to represent those masses in terms of volumes, volumetric flow rates, and densities. M is the total volume times the density of the fluid, and M dot is the volumetric flow rate times the density of the fluid. And we have identified the densities and the volumetric flow rates as constants. We haven't said anything as such for the total volume. Now let's write our balance equations with constant density assumptions. Density is constant. As a result, I'm going to take the out of the derivative, and my dm becomes dv over dt, and that is going to be equal to v0, we also taken this as constant, times rho that enters through the system boundaries minus v0 times rho that leaves the system boundaries. Now rho was constant, and I'm going to cancel them out from the equation, and I get dv over dt to be equal to v0 minus v0. This is going to be 0, and the solution of this differential equation will tell me that my total volume is not changing. So the derivation's purpose was to give you a hint about the underlying principles of constant density and constant volumetric flow rate. So when we say constant density and constant volumetric flow rate, that leaves the volume of our reactor constant. Now with this, I'm going to go back and I will rearrange the overall species mole balance, dNA over dt being equal to FA in minus FA out plus RA times V. And I'm going to solve this equation for you for the startup of a mixed flow reactor. Remember, our volume is constant. As a result, NA being defined as CA, and I'm going to drop out from the definition. I'll just label the concentration as CA times volume. And as a result, dNA over dt will be V. I have taken V out of the different derivative because it is constant, dCA Ca over dt. The other side of the expression is Fa in, remember V0 is constant, V0 times Ca in minus V0 times Ca out. Remember, I dropped out from the definition, from the identifier, minus plus Ra times V. Right? So I'm going to divide both sides of this equation by V0. To obtain tau. Remember, tau was V over V0. It was the space-time. dCa over dt, that is equal to Ca in concentration of the stream that enters through the system boundaries minus Ca plus R sub A. And we are solving these equations for a hypothetical A goes to products type of a reaction. And we define its kinetics as A minus R sub A is equal to K times Ca, following from the previous recordings. So I will substitute K times Ca minus K times Ca for the R sub A and my final differential equation. And I have, of course, a tau here. All right? And my final expression will be tau dCa over dt, that is equal to Ca in minus Ca plus minus tau K Ca. And I will rearrange and solve this equation in the other frame. So now let's divide our board for the problem definition on one side and problem solution on the other side. So here on this frame, I will carry out the mathematics to obtain an expression, and then I will discuss the final equation in terms of its physical significance. First, I will carry my differential equation here, dCa over dt, tau dCa over dt. This is equal to Ca in minus, now let me group the terms that have Ca. Ca 1 plus tau k. Remember, tau k was the Damke-Euler number. It was a dimensionless quantity. And now I need a boundary condition. My boundary condition will represent a stirred mixed flow reactor, which is initially filled with pure solvent. All right. At time t is equal to 0, Ca is going to be 0 because I have only solvent in this reactor. But I have a liquid. The tank is filled with the solvent. At time t is equal to 0, I start introducing my solute, my reactant, into the feed stream, and I monitor I monitor the product stream. Okay? My product stream is at the same concentration as the contents of the reactor. This is the condition of a well-mixed reactor, well-mixed flow reactor. Yes, now this is my boundary condition or initial condition at time t is equal to 0, Ca is equal to 0. So this is where I'm going to generate my solution. Well, this is going to need some rearrangement. I will collect Ca containing terms on one side of the expression and time containing terms on the other side of the expression. I have dCa over Can minus Ca times 1 plus tau k on this side, and I'm going to have 1 over tau dt on the other side. When I integrate both sides, I need to add an integration constant I will call phi. All right? This integral is fairly straightforward. Here I will need to make a change of variable. I will define a new variable. My new variable is going to be called u, which is equal to Can. And remember, Can is a constant. Minus Ca times 1 plus tau k. And as a result, if I take the derivative of u, this should be 1 plus tau k with a minus in front, dCa. So I'm going to take dCa from here in terms of du and substitute here to obtain integral du with a minus in front. Let me put the minus here. And let me take those constants outside the integral. 1 over 1 plus tau k divided by u. See, my integral has simplified. Let me carry out the integration on the other side. It is t over tau plus phi, the integration constant. This is ln u, and I will substitute u back into the equation. I will carry out this algebra as 1 over 1 plus tau k times ln of u, and u is this, Can minus Ca 1 plus tau k. Which is equal to t over tau plus phi. Now I'm going to substitute my initial condition at time t is equal to 0, Ca is equal to 0. So when time t is equal to 0, this term is equal to 0. My integration constant, Ca is equal to 0. This term disappears. I am left with minus 1 over 1 plus tau k times ln Can. That is my phi. Right? So I substitute this for phi, and I have an expression for t. T is equal to tau. I carried this to the other side of the equation. Times this was on this side of the equation. When it is carried to the other side, it lost this minus sign. So I'm going to have them in the same common denominator. 1 plus tau k times ln Ca in minus, it is this minus, ln, let me make this fancy bracket so that I will have my square bracket here, Ca in minus Ca 1 plus tau k, all the brackets. And I will do one more step of rearrangement. I will write them as ln, this divided by that. And I will just do a trick of having a negative term, and I will explain why I need to have a negative term in a moment. Minus tau divided by 1 plus tau k times ln Ca in divided by Ca in 1 minus Ca divided by Ca in. Let's keep our fancy and square brackets. Times 1 plus tau k, our square bracket and our fancy bracket. Actually, we don't need those brackets now. ln takes care of this. Okay? So this is our expression. Now we have an equation that allows us calculate how much time it takes in order to have a concentration of Ca, if our Ca in is this, if our space-time is that, if our rate constant is that. So this is the expression that relates time to the concentration. But sometimes we are more interested in how much time it takes for our concentrations to achieve a certain value. Now let me rearrange this expression for time. So I will get this space for the other type of representation of the unsteady state reactor operation. So let us take these to the other side. Let us take the exponent that we have now, 1 minus Ca over Ca in times 1 plus tau k is equal to, I took the exponent, e to the minus t over tau. Pay attention to this term. We will see this term very frequently, multiplied by 1 plus tau k. And of course, now we need one more step of rearrangement. Now we are after Ca, an expression for C sub A that is going to be equal to, I will swap those two terms in the equation, 1 minus e to the minus t over tau, 1 plus tau k. So this is one term, this is the other term, and then we have to multiply the whole thing by Ca in. Let me just do a little bit of housekeeping. I hope that this is going to be visible. Ca is equal to Ca in. So this is our final second expression. And this is the other one. This is our final first expression. And of course, both of them are going to be useful in answering different engineering questions. Now let's take this information in. Let's contemplate about their meanings, and in the next video we will have a graph, representative qualitative graph, that will show us how the concentration behaves as a function of time and the physical significance of these equations.